All right, guys, so this is hopefully going to be the third and final part of today's afternoon lesson. Okay, and I would say these are probably, anytime you guys have come across these questions, they're quite difficult sometimes, right? Or they at least give the impression that they're quite difficult, trying to find four variables, or four coefficients, I should say, right? So with this question, we want to determine the coefficients or constants a, b, c, and d so that the curve ax cubed plus bx plus cx plus d has a point of inflection at the origin. This is going to be important. Remember the origin is going to be 0, 0, okay? And a local max at this point, 2 and 4. Okay, so I would say being able to have some form of process when looking at these questions, right? I'd say if you see the point of inflection, you know that's going to be we haven't seen this before today, right? If you see the word point, or the series of words point of inflection, right, the phrase, you know that's talking about the second derivative, okay? And so I think like if I had to give you one, almost like if you're doing a physics question, we always say draw a free body diagram. If I had to give you one kind of idea here in tackling a question like this, I might say let's write out the original equation, whatever it might be. Oh, ax cubed, sorry. Write out the original equation and then derive it. Give me the two derivatives, right? You know that there has to be two derivatives because we're talking about the point of inflection. That's what we spent today doing, right? So let's derive it once and see what happens. We get 3ax squared plus 2bx plus c. That's the first derivative, okay? And the second derivative, if we were to derive this again, we're going to see 6ax plus 2b. Okay, let's put a little box around this because these are going to be useful and they're going to help us with our solutions, okay? Now we know that there's an inflection point at the origin. Okay, so why don't we, like this is, anytime they give you a question, like a point on a graph, that's information. You guys can plug that in. So why don't we do that right away? Right, it's telling us that there is it's being very specific in what kind of point it is, but it's still telling us that there is a point on the graph, right? Anytime you guys are given a point on the graph, plug it into the equation that represents the graph and see what happens, right? The function. So if x equals 0 and y equals 0, right? This is the origin, then we can plug that in to the original equation. So y, right, we're going to see something like, I don't know, 0 equals a times 0 cubed plus b times 0 squared plus c times 0 plus d. Well, what does this equal? Well, it gives us the piece of information that d is equal to 0, right? So there's one of our coefficients found right away. No issues, right? The second thing that you guys can do, we know because we learned this morning. Let's go up and look here. See this for points of inflection, right? It gave us a definition here. F double prime of x is equal to 0. That's for a point of inflection, right? F double prime of x is equal to 0. This is a point of inflection. Okay? Now we know that one of these exists because it told us, okay? So we can say, okay, well, let's take the second thing you can do here. I'll try to organize this in a nice way, okay? Here's number one over here. You know what? Here, let's go. I'll do this so we're not jumping all over the place. I'll move this over here. Okay, we'll go left to right. Top to bottom, left to right. So the second thing that you guys can do this. What's this, you ask? Set the double prime, f double prime of the second derivative equal to 0. This equation that you found. So 0 is going to equal 6ax plus 2b. Okay, but we know something in here, right? You know that this is obviously f double prime of x is equal to 0, but there's another thing in here as well. You know that this point of inflection is occurring at the origin, so you also know, sorry guys, one sec. Talking and writing at the same time, can't do that sometimes. That's equal to 0, the second derivative. Same idea up here. But we also know that it's occurring at the origin. So we know its x value is 0. So plug it in there. Well, 0 equals 6 times a times 0 plus 2b. Well, that's 0. So 0 equals 2b. So you know that b is going to equal 0 as well. Okay? Now, we know, because it told us, that there is a local maximum. Okay? There's a local maximum on this graph at this point. It told us explicitly. Again, it's told us in a point on the graph. So use the original equation, right, to see what you can get out of it, right? So we know number 3 here is going to be, we know x equals 2 and y equals 4. Okay, so take your original equation, f of x, and plug it in, right? Or sorry, y. Won't call it f of x, we'll call it y. Okay, so let's take the original equation, y equals ax cubed plus bx squared plus cx plus d, replace it with x is 2 and y is 4. Okay, well, 4 is going to equal a times 2 cubed plus b times 2 squared plus c times 2 plus d. Okay, what do we get? Well, we get 4 equals 8a plus 4b plus 2c plus d. Now you know, we already know, we know the fact that d is 0 and b is also 0. Right? So that eliminates, I'll do it in a different color so you guys can see. We know, because of these, d is 0 and b is 0. So what are we left with? Well, we're left with the fact we're going to get 4 equals 8a plus 2c. And if I were to rewrite this, I could, I don't know, divide everything by 2 just to make it a little simpler, right? We're going to say 2 is equal to 4a plus c. So we're really close. Okay? This is setting up for something that you guys have seen before. Okay? Now, there must be one other thing that we could do. Okay, and there is. The last piece is, step 4, before we actually solve this question, is, well, we have a local maximum, but recall what the maximum, and we spent tons of time looking at something like this, right? We know what is true about what is true at a maximum or a minimum. We know that the derivative of the function is equal to 0. Its slope is horizontal. It has no slope. It's equal to 0. Okay, so we can use this. We're going to use this equation, our slope equation, to solve this now, right? We're going to say, okay, well, that's great. We know that y prime is going to equal 0. Okay, so 0 equals 3ax squared plus 2bx plus c. Now, for the same reasoning as we apply down here, we know that b is equal to 0. So that is also going to disappear. And what are we left with? Well, we're left with the fact that, if I were to rearrange this, c would equal negative 3ax squared. Right? That's just for solving for c here. Right? So we know that that's true. So what could we do with that? Right? Okay, well, there is something else that we know too, right? We could probably actually do this quite nicely, right? We also know that the local maximum occurs when x equals 2. So not only do we know the fact that f prime of 0, the slope of the tangent at this point is 0, we also know that it's occurring when x equals 2. So we could say, okay, well, we could actually find something, we can make this expression even easier by evaluating when x equals 2, right? So we could say, okay, well, c equals negative 3 times a times 2 squared. All right, well, c is going to equal negative 12a then. Okay. So now we could do that. We could use this and plug it into here. Right? Where do I want to write this? I'm just trying to see what's going to be clear for you. Step 5, I'll say. Okay? I think the steps help. Plug c equals negative 12a into 2 equals 4a plus c. Okay, this is step 5. So that's what we're going to do. We're going to ultimately solve for a, right? We're going to see 2 equals 4a minus 12a. 2 equals negative 8a. A is going to equal negative 1/4. Okay, we now have 3 of our 4 coefficients, right? They're in green. We can now find what c is going to equal because I know what a is, right? Step 6 is use this equation, right? C is equal to negative 12 times negative 1/4, right? That went in there for A. And we can say, okay, well, C is equal to 3. Last step, because ultimately what did it ask for? Determine the constants. So what I would say, just to make your life easy, I'd say, okay, well, the constants, here's your original function, okay, with the coefficients in place. Negative 1/4 x cubed. What's the rest of it? B is 0, C plus 3x. You have told me what all the coefficients are on here. No problem. Okay, they're all in green. And then you've restated your original equation with those coefficients in place. Okay? I'm not going to deny the fact that looks incredibly complicated, but there is a series of events that have gone on there, right, that you can follow. All we have done is use the information that have been given to us in the question, okay, in the appropriate way, okay? So it requires you to know that the point of inflection is talking about the second derivative and that the local maximum is talking about the first derivative and how a maximum can only occur when there is a slope of 0. That's how we tackle these questions. You use what's in there and you always fall back on what you know. It's not going to tell you that a point of inflection, the slope of a point of an inflection is equal to 0. You have to know that. You also, the same way you have to know that a maximum occurs when the slope of a function is equal to 0 or a minimum. You're always going to fall back on that information, right? And you can use it in these questions to determine A, B, C, D, E, F, G, whatever you want, right? As long as they provide you with the appropriate amount of information. Okay, so I would imagine that might help you for even your second summative today, okay, that you're writing. So let's have a look at the last one, okay? It's basically the same thing. They've just worded it in an odd way, okay? And the derivative is going to be a little bit more complicated here. That's all, okay? So we want to evaluate f double prime of x at the indicated value and state whether the graph lies above or below the tangent. Okay, so what you're going to have a tangent. Just to contextualize this for you, because it wasn't necessarily clear to me right off the bat either. We're going to have a tangent, and then we're going to have a curve. Either it's going to be below the tangent, or it's going to be above the tangent. Okay, but it wouldn't make sense for it to be opposite like this. Because what is that? That's not, you know what I'm saying? This doesn't make any sense. Okay, so this is what it's talking about. It's talking about its concavity as to whether or not it's opening up or opening down, and it's just wording that in a way that it says above or below the tangent. So that's what we're talking about. Okay, we want to find whether, like, what's going on here. Is f double prime of x at x equals 1 positive or negative? That's going to dictate whether or not something is concave up or concave down. So that's what we're going to do here. But it starts with the fact that we have to find its derivatives, right? So we're going to take this. I think the easiest way to tackle this question is maybe not necessarily dealing with it in a product rule style of derivative, but I would switch this or sorry, not a quotient rule, I would switch it to a product, okay? So let's rewrite f of x in a way that it's kind of like a product rule, right? So we could say, okay, well, that's fine. We're going to get 2x squared plus 1, but we're going to get a minus 1 there instead of just a positive 1. So I've taken it from the denominator and brought it to the numerator. Okay, now let's do the derivative work. We have a power law, but there's also a function on the inside, right? So we're going to have to apply chain rule. So I'm going to bring the negative 1 down. So the first derivative is going to be negative 1 times 2x squared plus 1, right? And we know with power law, I have to subtract from the exponent. So it's going to be minus 2 because it was at negative 1. And then I have to multiply by the derivative of the inside as per the rules of chain rule, right? So I have to multiply by 4x. Okay, then we can do a little bit of cleanup. We're just going to say, okay, well, f prime of x is going to equal negative 4x times 2x squared plus 1 to the negative 2. Okay. Now, this is your first taste of, or maybe you've seen some of this in your homework questions. I haven't done all your homework questions, but this would be an example of where the more derivatives you take, the more and more complicated this stuff starts to look, okay? So you can now see I have two terms, right? Oops, switch this back. We have two terms here. So you know we're in a product rule situation, right? So I have two functions multiplied by each other. So when I go to find the derivative, I'm just going to write this here. We're going to have to find the derivative of f of x and multiply it by the original g of x plus f of x times g prime of x. Okay? And this is getting more and more complicated. This is just to highlight something here, okay? I sometimes, even to this day, this helps me so that I don't forget what's going on. Maybe I'll draw that in a nice box. Okay, so this is a reminder to myself, right? I got to derive the first one, right? So let's do that. F double prime of x is going to equal the derivative of the first piece, f of x. Well, that's going to be negative 4 times the original 2x squared plus 1 to the negative 2. And I have to add the original f of x function, negative 4x. And then I have to derive g of x. Okay, so we're going to get, okay, well, we get negative 2. And then we're going to get, you might want to put this in square brackets just to, you know, separate it for yourself so you can see. Negative 2 times the inside of the function, plus 1, minus 3 now. And then this has to be multiplied by the derivative of the inside. Again, we're going to get 4x. Okay. So we can do a little bit of cleaning up here, right? We could say, okay, well, f double prime of x is going to equal negative 4 2x squared plus 1 to the negative 2 plus negative 4 times 4 is 16 times, oh, sorry. So I'll write this down. We're going to say negative 4 times 4x is going to be negative 16x, and then we're going to multiply that by the negative 2. And so we're going to get 32. Okay, so I'm going to add 32x, and then that's going to be multiplied against 2x squared plus 1 to the negative 3. Oh, and sorry, it's x squared. Sorry. X squared. I missed that. Because it's 4x times xx is going to make x squared. Okay? So, you can see how the derivatives get more and more complicated, right? Well, you got to ask yourself, okay, well, what's the most number of, the largest number of what I see here? I'm going to highlight it in a different color. You've got minus 2 here and minus 3 here. right? So what's the least number of this piece that you could take out, right? Well, you could take out you could even take out a -4 as well, because 4 goes into 32. So we'll take that out. We're going to write -4, and then we know we're taking one of these yellow pieces. How many is the question? So we're going to write 2x squared plus 1. And turns out that you can take out -3 of them, right? The greatest number of them, right? And then we can say, okay, well, what's left after I do that? Well, I get 2x squared plus 1. I have one of those left now. And then minus 8x squared. Okay, so we're going to see -4, 2x squared plus 1 to the -3 multiplied against 1 minus 6x squared. Okay, and then therefore, this is a long derivative, guys, but f double prime of x, sorry, it's going to equal 4. We can clean this up. Okay, we can say it should be negative, I think, over. Oh, one sec, I know what happened. I know what I did. You can factor out a negative from in here, and we're going to rewrite this. We're going to write 4 times 6x squared minus 1. This is you'll notice the difference between these two. I factored in a -1 and they canceled. Okay. Over 2x squared plus 1 to the power of 3. This is your final double derivative. Okay. And now, now guys, we can say, okay, well, we know what the derivative is. And we know, because it told us, we want to find out what the actual value of the second derivative is at x equals 1. So if I evaluate the second derivative at 1, we're going to find out what's going on. Okay, we're going to see, okay, well, we're going to get 4 times 5 over 27, which is going to equal 20 over 27. Well, what's this mean? Well, notice it didn't come out negative, right? It's telling us something. I don't really care about what the number is. I care about the fact that f double prime at 1 is greater than 0, right? Which tells me, if you recall, we'll go back up. If f double prime of x is greater than 0, we know it's concave up, right? So we know concave up. What's this mean relative to the wording of the question? Well, recall what I said at the very beginning. Here's our slope of the tangent, and there's our graph. It does not make sense for it to be above the tangent and to be opening down, right? Or concave down. So what's this mean? Well, it means that close to, and we'll resketch this down at the bottom of the sec, but it means that the graph is above the tangent. Okay, so it's just some odd wording there, okay? And we could find, I don't know, we could find a particular value. Oops. We could find a particular value. Oops, I don't want that there. Let's save me some space. Okay, we could find a particular value, sorry, that let's say f equals 1, f prime equals 1 is going to equal -4 over 9 if we were to plug that in, which means the slope is decreasing, right? The function is decreasing. And if we were to find f at 1, remember we're just using the point that's given to us, we're going to get 1 over 3. Okay, so we could plot this. So let's draw a rough sketch. Okay, at 1, at x equals 1, we're going to get 1/3. So something like right in here, right? If this was 1 up here, it would be 1/3 of the way. And we know that the graph is going to do something. It's decreasing when it approaches here, and it's going to be concave up, right? We know that if this was the tangent, like let's say we had the tangent at x equals 1, we know that the curve is going to be above the tangent. Okay, but it's the slope, negative slope, and the curve lies above the tangent, so it's concave up. Okay, guys? Kind of a nasty question, but only really because of the function that was given to you. Okay, it just made the derivative was a little bit more complicated, but remember, that's really the only way we can make these questions any different from one another, right? Is either in the information that's provided to you or how complicated the function actually is, right? And that's what it comes down to, right? So you guys have some questions posted. I posted some questions in the textbook to help you answer some questions about concavity, right? And producing some of these graphs. Just to relate this back to the investigation that you guys would have done on Friday morning. If we're looking at concavity with this lens now, and we relate that to acceleration, right? Because I know we talked about that this morning as well. If something was concave down, right, so the second derivative was less than 0, we now know that that means that the acceleration is negative and the object is slowing down. If something is concave up, it would mean that it's accelerating and it's picking up speed, right? So that's your relationship between the second derivative and an acceleration, the work that you did from Friday. Okay, I'll post the solutions to that as well. I forgot to do that. Okay, so you guys let me know if you have any questions. That's pretty I know there's a question on your summative today that deals with stuff like finding the ABC values and D values, so that this video might help you with that as well. Okay, remember, it just comes down to here's your function, here's the derivative, and using the information that you know because we've studied it to your advantage, okay? And being very systematic in what you do, okay? And using not only your previous knowledge, but the information that's given to you in the question, okay? So that's that, okay? So you guys let me know if you have any questions with this, and hopefully that helps. If you guys watch this, it helps with your summative question as well, okay?